Hello, I'm SangBin. I'm a software engineer at Anyscale. Today, I'm going to present data processing on Ray. What is this talk about? The talk is primarily about Ray and how it evolves over time to support data processing. I'm going to go through why data processing support is important for general purpose systems like Ray, as well as what kind of architectural changes we've made over time to support that. Let me then introduce myself first. I'm a software engineer at Anyscale, which is the company that's backing Ray. I'm also a Ray committer and have been working on Ray over the past year. I have primarily worked on Ray core to support data processing lately, and which is why I'm having a talk today. Then let's start from why we need a general purpose system for data processing. In the modern ML infrastructure, there are lots of complexities in composing different types of workload in different systems. For example, this is the one I actually have seen in the industry. First, it needs to run ETL type of jobs using the Spark cluster for feature processing or some pre-processing. Load and shuffle the data that's written to Parquet into the training cluster. Like in this example, it uses Horbot. And after the training, it needs to do the hyperparameter tuning in the different systems. In this case, is Ray and also the Ray tune. There are also many cases where during the training job, it sometimes needs to run another pre-processing or shuffling workload back into the Spark cluster, which can actually add a lot of complexities when this sort of different composition increases in the industry example. Then what are the problems? Firstly, job composition across multiple different systems can actually increase the complexity a lot because it requires to maintain the multiple systems, organizing workflow of different jobs and scheduling them, and also taking care of these job dependencies and failures that happen among them. At the same time, managing multiple different systems can be incurring really high maintenance costs. Because there needs to be a team that maintain different systems, and each of team needs to understand how it works, how it operates, how to debug, and things like that. And usually, when you want to make multiple systems to communicate, it's usually not efficient because you always need to pass intermediate layers like some files, these Parquet files, like distributed file systems and things like that. And this can be very inefficient if you can actually solve all the problem like pre-processing, training, and things like that in the same cluster, all within memory when you have enough memory capacity in your training cluster or data processing cluster. Then what if you have a general purpose system? If a single system can run different type of workload, it can actually remove a lot of complexity we just go through. For example, instead of actually grouping the job, depending on what type of workload it has, which needs to be run in different systems, we can more logically group the job so that we can simplify the dependencies between jobs. It's also, if you can run multiple different workloads within a single general purpose system, there is going to be less maintenance burden because you just need to understand one system, operate one system, and also debug one system. That means you just need to learn one system in this case. And as I mentioned, the optimization is easier because if your data processing workload and also the training workload, if all of the results from the data processing can be cached in memory, there's no reason to actually pass the intermediate layer, and you can just directly pass data using the memory, which is a lot faster. Also, as you can see, this type of system composition could become like this with a single general purpose system. And you can run different libraries like ETL library, load and shuffle library, training library, and tuning library, all on the same systems. Now, what could be a good general purpose system candidate here? I'd like to introduce Ray as a solution for this problem. Let me actually briefly introduce what Ray is. Ray is a simple library for distributed computing. It's also general purpose, which is why we'd like to use this as a solution. It also has a great ecosystem of libraries which enable all the workload that we just described. And it's also written in very high performant way. If you're very interested in deep details about Ray, you can also check out the last year's PyCon talk. But I'm also going to introduce more about Ray in this talk. Okay, then let's actually learn a little bit more about what the Ray is about. Firstly, Ray provides simple APIs to write distributed applications. So normal Python programs usually consist of function and classes. And in this case, you have two functions, reading array from the file and also add that arrays together. And this is another class example. You have a counter class, which you just define it and you can increment the internal attributes using the increment method. This is very simple programming model and everyone understands if you're writing code. But if you actually want to run them in parallel in distributed systems, how would you do that? This becomes a much more complicated problems. Fortunately, Ray provides really intuitive APIs to support this. So in Ray, functions becoming task and class becoming actor just by adding a decorator called ray.remote. And once you decorate your functions, you can invoke them by calling .remote for each function and class. And these functions are basically executed somewhere in your distributed systems in parallel, and it's returning the future. And later you can actually obtaining the results by calling an API called ray.get on top of the future that is returned. And the same thing applies to the class. The class, once they are decorated by ray.remote, they becoming an actor. And this means this class is standing somewhere in your distributed systems, and you can communicate with that through the function .remote. Secondly, Ray is a general purpose systems. It supports both stateless and stateful computation, which are basically the primitive operations for building the distributed systems applications. For example, using the stateless computation like tasks, you can easily build distributed data processing library that is doing some ETL type of workload, or it's also possible to build some scientific parallel computing workload. If you use actor, it's also possible to even further optimize your applications. And in some cases, if you need states for your distributed applications, you can implement using actors. For example, RayTune is primarily written with actors, and it basically uses a parameter server that is done using actors. And also things like microservices type of applications can be written as actor. For example, RayServe is written primarily by actors, and there are also many other actor frameworks like Akka or Dapper. So third, Ray is an ecosystem of libraries. So Ray is a framework for distributed computing, and it provides the primitives for distributed computing and took care of scheduling, fault tolerance, and RPCs for the libraries, which allows you to write distributed applications of machine learning lifecycle end to end. For example, we have like a native libraries for some of critical machine learning workloads, and also many other third-party integrations, all running in scale on top of Ray. Ray is also a highly performant system, and it's very scalable. It's basically written, it's Python native, but the core part is written in Python as well as C++. So all the critical path is very fast, and it's not restricted by the global interpreter lock. And it also has fast scheduling architecture. So it has decentralized scheduler, which means your scheduling performance is not going to be slow when you actually scale up. And it also has built-in distributed object store, which has the shared memory and zero copy read optimization, which means you can have much efficient memory usage when you're using Ray. All these features clearly indicate Ray can be a great solution as a general purpose system for this end-to-end ML lifecycle. So this is the same example, but on top of Ray. So you can run Ray, and you can do the ETL job using Spark on Ray, and you load and shuffle the data using Ray ML dataset APIs, and also you can training using Horovod on Ray, and you can tune the machine learning model using RayTune. Ray was originally very ML focused, but we've had drastic improvements over the last year, and that's something I'm going to talk very soon. But as a result, we've been able to support many data processing third-party integrations on top of Ray, such as Modin, which is a distributed pandas, and also Dask on Ray, which is very useful for anyone who's using NumPy and pandas, and for other famous data processing libraries like Mars or Spark. So this is a typical example of you use all of the workload at the same place. So in this case, it uses Spark on Ray, as well as the torch estimator. So you can actually use the Spark data, create a Spark data frame here, and you can pass them to estimator and train here. So this is an example of running like a data processing workload and machine learning workload within the same cluster. It has the same job. Before going to the next section, let me explain how Ray was last year. Ray was very ML focused, and although it was really good at running ML workload, the data processing support wasn't robust enough because Ray wasn't supporting some of important features to be a great and robust data processing backend. And this is something I'm going to cover from now on. Okay. So let me first go through what types of data processing is out there. Firstly, the most common data processing workload is ETL type of workload, which basically extract information from some files and transform the data into different format and load them into different files. Usually people write jobs that run over hours for ETL type of workload. Another type of workload is the data ingest type of workload. So if you finish your ETL job, the result is written to some files and you need to ingest the data into ML clusters in order to train or do something else. And there are also analytics type of data processing, which heavily uses things like SQL, and it's usually used by people like data scientists and with things like Jupyter Notebook. And there's also streaming processing, which has pretty unique requirements. And specialized systems like Flink is supporting streaming processing. For Ray, we'd like to make sure Ray be the best choice for the end-to-end ML lifecycle right now. So in the short term, we're going to focus on the top two workloads, ETL, and also the data ingest, which is pretty important for the ML lifecycle as I described in the beginning of the presentation. Okay, then let's actually think about what are important features data processing backend should have. Firstly, it should support seamless distributed execution. For example, we should be able to run stateless functions in the distributed systems, and it should handle what distributed systems should do. For example, it should scale, should be fault tolerant in component failures, handling network operation, as well as object transfer across machines. Secondly, it should support robust distributed memory management. So it's not going to crash when you have a really large memory usage that is even bigger than the capacity of memory that your cluster has. Then how did Ray look like before? It satisfied the first requirements, but not the second one very well. So Ray is designed to be very highly performant and general purpose. And all of this seamless distributed execution, as I explained before, is supported very well. Whereas the robust distributed memory management wasn't really not well supported. For example, the out-of-core processing wasn't possible previously, and the scheduling didn't really respect the memory usage of each machine, and it doesn't really do the locality or scheduling as well. And there was no admission control respecting the hard memory limit for each machine. To make sure Ray supports data processing, we wanted to make sure it has robust distributed memory management. Then I'm going to explain how we actually achieved it from now on. So firstly, what we try to do is to make sure the distributed shuffle works really well on top of Ray. Before we go dive into what we've done, let me actually explain what is distributed shuffle. Usually in distributed systems, data set is usually stored in partitions, with each partition holding a group of rows. Shuffle is basically the operation over the data set that redistributed data across its partitions. It's pretty important operation for data processing because it is quite commonly used for many different distributed data processing algorithms. Like for example, when you're running sort, like distributed sort, it requires you to run shuffle under the hood. So this demonstrates actually how this works. So usually it has two phases, the map phase and reduce phase. And usually map phase create objects. As you can see, they're creating 4 different objects. Oh, by the way, you can think circle is a task, Ray task, and square or Ray objects. And you can see each of the first object is going to the first reduce. The first object in this format goes to the first reduce, and which means the objects are now redistributed in the reduce task. So you can do some different operation with the shuffle data. So then why we focused on supporting distributed shuffle? Yeah, it is because distributed shuffle stresses data processing systems memory management layer very hard. It's because it requires a lot of transfer of objects between tasks these actors. As you can see, every object has to be transferred to different reducers, meaning there's going to be a lot of object transfer. And usually the size of data is way larger than the memory capacity of your cluster, meaning you have to support out-of-core data processing to support distributed shuffle robustly. It's also very easy to test because we can easily scale it up. For example, we can try from like 1 GB, 10 GB with a less number of partitions. By the way, in this case, there are 4 partitions. And you can easily scale up to like 1 TB, 10 TB, 100 TB with thousands of partitions later to actually stress your system to the end. So last year, Ray couldn't really handle heavy distributed shuffle workload. But we have made a lot of improvements over the year. And that's something I'm going to explain from now on. The first improvement we've made over the year is the scheduling improvement. So previously, Ray didn't have locality-aware scheduling as well as memory-aware scheduling. So previously, Ray didn't really respect memory usage at each machine. But now what it happens is it basically knows how much memory is used per machine. And it basically prefers to be scheduled to the machine that uses low memory. And another optimization we've made is called locality-aware scheduling. So locality simply means when you're scheduling Ray tasks, you want to schedule on the machine that already has the objects that are needed for tasks. And previously, we don't do that. And if we don't do that, the problem is all of these objects have to be transferred and copied to the machines that schedule tasks. And this was very inefficient. So now every Ray task basically knows what kind of objects it requires and where they are. So we can actually do locality aware scheduling and schedule on the machines that already have the largest number of object size for the task. And this will eventually minimize objects copied across different machines. The second improvement we've made is to enable out-of-core processing. So we basically implemented something called object spilling, which spills Ray objects from object store, Ray's built-in object store, to external storage like disks or S3. This is very critical for supporting distributed shuffle workload because distributed shuffle usually has more data size than the maximum capacity of memory. So we usually have to rely on external storages. And I'm going to explain how object spilling works on top of Ray from now on. So this is an example where shuffle is running without object spilling. So let's see from the map phase first. So in the map phase, basically this big square is a worker, and this circle is a task. So these two map tasks are scheduled, and they're creating objects for like this to the object store. And in the reduce phase, you basically want to redistribute. So these reduce tasks are scheduled, and you can see the first square in the first map task, and the first square in the second map task is going to be gotten by the first reduce task. You can see this light blue and light purple is obtained by this reduce task, meaning now this reduce task can do some operation with shuffle data. Then how they work when object spilling is required? Let me start from the map phase. Note that this is the same as this progress, but it requires object spilling as well as there are more map tasks. So the difference is we have external storage here. So now these two tasks are scheduled first, and they create objects. And now a new task has to be scheduled, and you just realize this needs to create 8 more objects, but there's no capacity in memory. So what Ray is doing is it smartly chooses objects to spill, and it spills them to the external storage. So it's gonna make space to create objects for this task. And it just repeats until every objects are created. Then what's going to happen in the reduce phase? Note this is the same process as this reduce phase. And we have more tasks here. So first, this is the state after all the map phase is done. So now two reduce tasks are scheduled, and you realize this needs these 4 objects, and this black task needs these like a thick 4-color objects that are shuffled. So the first thing is it has to restore the object from the external storage into memory so this task can access. So Ray smartly chooses which objects are not needed anymore from the shared memory object store, and it spills to the disk first. And now in the empty slot, it basically restores the objects properly, so that you can actually schedule tasks that are in the external storage. So you just realize all of the objects are already here, and basically repeats until every tasks are done. So the last improvement I'll demonstrate is how we improved our memory management layer. In summary, Ray respects a hard limit for the distributed object store. So what does that mean? There are three things that basically we implemented. The first thing is it detects when there is the memory pressure. And also it guarantees the progress when applications run out of memory by taking the proper actions. For example, the task has to be scheduled and it needs to have some number of objects that are they have to fit into the memory. Then it properly evicts unnecessary objects or spilling objects with the right priority. So it's going to make space always so that all the tasks in the system can actually be in progress. And lastly, we also implemented admission control when scheduling tasks, so that it actually respects the total limit. So to limit the total memory used. So it doesn't schedule the task if it realizes if the task uses more memory than the capacity of the memory. And I'm going to demonstrate how the last part is working. So this is the state after the map phase is done. And as you can see, these two reduced tasks is going to be scheduled. Note it has enough CPUs, as you can see, these two tasks are now queued and this top and bottom is now scheduled. So we know these 8 objects are 8 object needs to be restored into the objects. But what you notice that there are only 6 slots. So there are 8 objects, only 6 slots, meaning you're not able to actually fit all of the object to the memory. But let's see what's going to happen in this case. We try to retrieve object for each task. Repeat. And you realize the last 2 objects that is required for each task cannot be fit into the memory, meaning both of tasks cannot be in progress. So there's deadlock. And another problem that this kind of workload can have is if you, for example, spill this 2 green again and restore this 2 orange again, you're still not in progress because each task needs 4 objects that are needed for each task to be in memory, but it never been there. So this happens again and again. So it basically spills again, restores again, spills again, restores again, until there happen to be 4 objects for this task to be available in this memory. And that's very inefficient. So how did you solve the problem? Now Ray has decentralized schedule. Ray decentralized scheduler is also decentralized memory manager. And Ray doesn't schedule tasks if the task input require more memory than its capacity after it's scheduled. So let's see what that means with real example. So previously we just try to restore objects for each task, but now Ray smartly knows that if we put objects for both tasks at the same time, it's gonna be out of capacity. So we basically try to restore object for the first task first. And then the first task is done, and it knows that the second task needs these 4 objects, and the first newly scheduled task cannot have objects at the same time because it also requires 4 objects. So it only restore object for the second task and repeats. Yeah, so for more detailed information, so we didn't cover every detail about how this is implemented. So if you're interested in more detailed implementation information, check out our white paper. So after this improvement, now Ray is supporting both requirements to be a robust data processing backend, the seamless distributed execution, as well as robust distributed memory management. As a result, we could support many third-party integration very well. And we've actually seen many positive benchmark results from these libraries. And also we recently succeeded to run live 100 terabyte distributed shuffle workload on top of Ray. And we are also going to further investigate to improve the performance as well as reliability of systems when running very stressful shuffle workload. Okay, thank you so much. It was a real pleasure having a chance to present at PyCon. If you're interested in Ray, please visit our GitHub page and give a star, or visit the Ray discourse for asking questions. And also there's gonna be Ray Summit next month, which is free. So please join Ray Summit if you're interested in Ray. And if you're interested in Anyscale, which is the company that's backing Ray, we are hiring right now. Okay, thank you so much.